As a result, you'll burn just a little more fuel. As a result, your fuel tanks have to be a little bigger and you have to carry a little more fuel. As a result, the structure carrying the fuel tank has to be a little bigger. As a result, the whole structure of the wing has to be a little bigger. As a result, the fuselage has to be a little bit bigger. As a result, everything grows and it gets a little bigger. As a result, the whole airplane gets a little heavier. And you're probably wondering what I'm saying. What I'm trying to say is, when you add a pound to the aircraft, you actually end up adding 4 or 5 pounds by the time you take into account. If you want to add a pound of useful load, by the time you add in, if you want to add a pound of useful load and maintain the same range, performance, rate of climb, and everything else, by the time you're all said and done, you end up adding about 5 pounds. Because it takes a little more power, a little more fuel, a little more structure, a little more this, a little more that. By the time you're all said and done, you add about 5 more pounds. And when you build airplanes and develop airplanes, you actually pay by the pound. Actually, you pay by the speed and by the pound. Okay? The faster the airplane goes and the more it weighs, the more it costs you. So, here's just some things to remember. We can't do the whole conceptual design in 45 minutes, so we will look at one of the most important jobs in doing a conceptual design, and that's the design of the wing. And we'll hope here to learn just a little bit about some of the basic terminology used in designing a high-performance wing, some basic aerodynamics, and a little bit about basic performance. And we'll work from a familiar database of Workplace Bonanza, not because I just went out and bought a Bonanza, but because it's a common airplane, and everybody's familiar with it. There's a lot of data available on it, and it's just something that I think that I thought we could use. Now, the approach is going to go something like this. I take an older model, actually a B model, and we're going to assume that we want to maintain, for our mission requirements, the same useful load as this B model 35 Bonanza. Okay, so we're going to want to maintain the same useful load, that's our design requirement, and we want to maintain the same stall speed, okay, and we want to maintain the same takeoff gross weight, which means we basically want to maintain the same takeoff performance, the same useful load or payload carrying capacity. Okay, so in order to be able to just learn a little bit about this whole process and show you a little bit about wing design, I picked a practical application, and I picked a couple things to hold constant. Okay, so we're going to hold those things constant. And what we're going to do is we're going to look at designing a new wing. Also the power loading. The power loading is going to stay constant. Okay, so we're just going to set the power loading as it is. We're going to set the useful loads as it is, set the takeoff performance as it is, and we're going to look at improving the wing design to see what we can do for the overall performance of the airplane. Okay, now, by improving the wing design, we can get an airplane that will go faster and have a lot higher range. So we'll take a look at doing just that. Okay, so let's go ahead and walk through that. I'm going to throw out a few basic equations. Again, we come from a broad background here. Many of you may be engineers. Many of you may not be engineers, but may be aircraft designers that are really good at math. So I really don't know where to begin, where to pick it up. So I'm going to start with some basic equations that, as an aircraft designer or a home builder who's looking to design an aircraft, these are probably some equations that you would find useful. And they're not what we use a lot is in calculus is something called differential equations. Okay, we're not going to get into any of that. Okay, these are all just algebraic equations, okay? So let me take a look, let me show you a few of them, and let me tell you what they mean. If this is the first time, is everyone, how many of you have seen this before? Oh, a lot of you have, okay, well okay. Again, a lot of you have seen this, I apologize for going back to square one, but okay, you basically have the lift coefficient, okay? The lift coefficient is a non-dimensional form of the lift of the wing. Why do we use the lift coefficient? Because it can be used to describe the lift characteristics of a wing, and it's not dependent on the particular velocity or the size of the wing. It is equal to the lift divided by 1/2 times the density times the velocity squared times the reference area of the wing. Okay, so that's our lift coefficient. The drag coefficient is merely the drag. Okay, lift is going up, drag is going back, and it's merely the drag force divided by the same thing. So again, a very common starting point. The total drag is a component or a mixture of two things. It's the zero lift drag and the induced drag. Okay? Now the induced drag is a drag that is strictly a product of the lift. If you have no lift, you have no induced drag. The zero lift drag is also, I call it zero lift drag. Now, in different textbooks, sometimes it's called different things. I forget what Raymer calls it. I don't know if he calls it that or not. I know McCormick does. Rossman does. The zero lift drag is basically the drag due to everything except the lift. Okay, and it's also been called the parasite drag, I think. And it's the cleaner the aircraft is, the less zero lift drag that it has. Okay, so if you have and I'll show you some examples. If you have an airplane that has a lot of rivets, and a lot of things sticking out, and a lot of antennas, and very few bearings, and fixed landing gear, and big struts hanging everywhere, and all that, it's zero lift. The drag coefficient will be high. And if it's really, really smooth, it's composite, and the surfaces look like glass and everything else, like a water glider, it'll have a zero lift drag coefficient that's really, really low. So those are the two components of the drag. The induced drag is something that we calculate from this formula here. Now, it's a function of the lift coefficient squared. So as the lift coefficient goes up, we actually square that to get the induced drag. So if you double the lift coefficient, then the induced drag coefficient goes up by a factor of 4. Okay, so it's a function of the square. We divide it by these three things. Pi stays the same. The aspect ratio is in there, and then we have something very important here called the wing efficiency factor, or Oswald's efficiency factor. And I'll talk about that a little bit. The aspect ratio is very important. If the aspect ratio goes up, this number gets smaller, and the induced drag goes down. Okay. Therefore, the higher the aspect ratio, the lower the induced drag. So, why not build wings that have an aspect ratio of 100? That would make that number really small and just fly around with wings with an aspect ratio of 100 everywhere. Instead of 5, like a Cherokee. Well, actually, this is, been debated around, many tables a long time by aerodynamicists. What do we do with the aspect ratio? We want it higher, but if it gets too high, we got a real big long wing that just flaps like a piece of spaghetti, and that doesn't work very well. So it's a compromise. It's a compromise. In aircraft like the ones we fly, general aviation aircraft, at our cruise speeds, where we cruise, okay, typically most of the drag, I don't have a pointer, and this is important to realize, most of the drag comes from CD0. About, 75, 80% of it comes from CD0, and the rest, 20% or so, comes from CDI. Sometimes only 10%. So the induced drag is not a huge component of the total drag. So making the wing a really high aspect ratio wing will help a little, but it really doesn't help a lot. So that's why the Cherokee has an aspect ratio of 5. But it does help a little, okay? Now, and I'm trying to get you to think like the designers kind of think. If you start to make the CD0 small, okay, in other words, you go from the Cherokee to, which is a very draggy airplane, to a new modern composite airplane, which has a much lower CD0. Okay, now the component of CD0 is not 80%. Now it may come down to about 60%. So now the induced drag moves up to about 40% of the total. So now, oh my God, the induced drag was only 10%, on the Cherokee, but now the induced drag is 40% of the total. So, now we can't, the aspect ratio, we can't kick the can down the road anymore. Now we got to start really taking a look at this. And that's exactly what happens. So the airplanes get cleaner, the CD0 goes down. Now we got to start thinking about the induced drag, and now we do. And the aspect ratios all of a sudden aren't 5 anymore, they're now 10 and up. And it's not just us. It's, the DC-9 that I flew had an aspect ratio of about, I think the DC-9 was about 8. And then the Airbus A330 has an aspect ratio, I think it's over 10. That's huge. I mean, for a large airliner where you have a highly swept wing, I mean, to go over 10 with an aspect ratio is a really tough thing to do. It's huge. So the same thing happened. The zero lift drag came down, the induced drag became a major factor, and all of a sudden it became really important to make high aspect ratio wings and put winglets on them and everything else. So anyway, those are just some of the things that become important that we think about. Excuse me, my wife's in Oshkosh, which I'll call you later. Okay, the induced drag, like I said before, it's a function of the aspect ratio. I won't go into all the specifics. Some of you may know this, but if you have a low aspect, there's many ways of looking at the induced drag, but if you have a low aspect ratio wing, the air tends to spill over the wingtips kind of fairly easily and creates these vortices, and that gives you a lot of induced drag. One way to look at its energy, if you have a very strong vortex coming off the wingtip, it takes energy to create that vortex, that swirling, and that energy has to come from somewhere, right? So it's coming from the engine, essentially, from its thrust, EI drag. So low aspect ratio wing gives you a lot of induced drag. High aspect ratio wing, very low induced drag. And this here is really an awesome picture that I found. Look at this. He's flying just above the clouds, and which I've done 1,000 times, but I never had a rear view mirror where I could look back and see. But look at the vortices rolling up behind the wing. You can really see the effects of the vortex formation, the induced drag. So anyway, that's where it comes from, and it's something to think about. Anyway, just another way of looking at induced drag. I won't waste any time on this. We are always thinking about the maximum lift-to-drag ratio. It's very important. The maximum lift-to-drag ratio, fortunately, boils down through the aid of calculus, being able to write a differential equation and take a maximum instead of a 0 for those that had calculus. Because of the beauty of calculus, we can come up with L over D max, and it's very simple. Pi ARE over CD0. Ideally, and
if you remember anything, remember this. Ideally, we would love to fly all of our airplanes around at their maximum lift-to-drag ratio. For a lot of these airplanes out here, the maximum lift-to-drag ratio is 20 and higher. And we'd love to fly them at their maximum lift-to-drag ratio. But the problem is their maximum lift-to-drag ratio occurs at a speed of, maybe 120 knots, where we'd like it to be, 220 knots. So how do we make the maximum lift? How do we keep the L over D 20, but make the speed for the L over D max 220? How do we do that? Huh? Well, yeah, that's exactly what I'm going to do. Well, that's exactly what I'm going to talk to you about. But without doing that, there's only two ways you can do it. Okay? One way is to go up and fly where the air is really, really thin. But the problem is, these airplanes have a tough time at 40,000 feet. But if we could get up there, we could fly at L over D max 220 knots. Why do you think all the airliners are at 40,000 feet? It's so funny, everybody says airplanes fly high because, the drag is so much less. I have to laugh, it's so funny. The lift-to-drag ratio for, an MD-80 is 17.4. It's 17.4. I mean, it's 17.4 whether you're at sea level, whether you're 1,000 feet below sea level, or whether you're at 35,000 feet. It's still 17.4. That means it's going to take so much thrust or drag to pull you along no matter what altitude you're at. It makes no difference. The drag is no less up there than down here. The key point is that in order to be at that speed where you are at L over D max, if you're at sea level, it's 190 knots. If you're at 35,000 feet, it's 444 knots. That's the difference. You reduce the density. And by reducing the density, you change the angle of attack. So you can drive the wing up to the angle of attack, where you're now at an L over D max of 17.4. Bingo, that's why everybody's up there. So anyway, back to what we were talking about. If you have an airplane like we have out here, and you want to cruise at L over D max, you want to fly with an L over D at 20 and hardly, run on fumes at 220 knots, you can do that. But the problem is you got to do it where the air is really thin, so you have to go up to 40,000 feet, or you have to go out with a saw and you have to cut off at least half of your wing, probably more. But that's a problem, because when you come back to land, your stall speed is no longer 70, it's now 120, so that doesn't necessarily work either. So we have a problem, and a few more equations. I won't spend much time on these, and I'll tell you what we're going to do to compromise a solution so that we have an airplane that will do all of these things really well with the new wing design, and we're going to solve that problem. I'm going to tell you how we're going to do it, because we're airplane designers. We're going to design a high-performance light airplane. We're going to fix this problem. That's what we do. We think, and hopefully by talking about a lot of these things, I can pass some of these thoughts along to you, so we kind of get the train of thought of how to think these things through. Anyway, we have a couple other equations here that come in handy. I won't spend much time. We have something called Bouvet range factor. It's useful in figuring out how much fuel we burn during cruise. That's primarily the equation we use to calculate our range and fuel burn requirements. Okay? And it has a few things in it that, of course, you might anticipate needing, such as the SFC in your motor. Very important when it comes to fuel burn. MP, that's actually eta P. Engineers, we love Greek symbols more than the US symbols, so that's eta P. That's the efficiency of the propeller. Put a really poor prop on your airplane, it's not going to do very well. So that shows up. And then, of course, our friend, L over D, the lift-to-drag ratio, huge. Very important. So, anyway, those are some really important equations. Aspect ratios. The Cherokee is, I just have a couple of pictures for the heck of it. Okay, it's 5.7. I was off a little bit. It's not 5. The regional commuter, 12.5 with no struts. So they made huge improvements with that airplane. Obviously, the decision was made that they could make huge gains in efficiency by going to that higher aspect ratio. And then for the glider, you have to cruise at L over D max, even if it's really, really slow. If you want to, go from State College, I don't know where in Wisconsin, but gliders near Penn State, where I got my first degree, they actually glide from Penn State to somewhere down in Tennessee along the ridge. And the way they do that is they go up in these really efficient gliders and they glide at their L over D max. And I talked to the guy, Tom Knopf, who set all these records doing it, and he says the key is you always glide at L over D max, even if it's a really, really slow speed. You just take your time. It always stays at L over D max. There's an angle of attack. And so you put these high aspect ratio wings on here, you get a really high L over D max. And you fly slow enough to maintain that high L over D max, really high, and away you go. So, okay, that factor E, we cannot discard that and throw it out the window. That is very important. That is called Oswald's efficiency factor. And it plays a big part in our induced drag. Okay, what is it and what in the world does it mean? I gotta just tell you a little bit about it. Okay, it's the wing efficiency factor. For a perfect elliptical wing, such as the British Spitfire, Max Monk, a great pioneer of the father of aerodynamics to me, him and Prandtl, they're really it, he figured out that elliptical wing has the ideal efficiency factor of 1. If we put winglets on it, we can actually get a factor greater than 1, which is really amazing. Now, if we have a rectangular wing, which is really bad, we're down to like 0.75, okay? That's a 25% reduction in E, or a 25% increase in induced drag. That's not very good, right? Okay, so does anyone ever see a jet transport flying around with a rectangular wing? Yeah, there's your answer right there. 25% more drag, reduced drag, you wouldn't have a job very long if you designed that wing. So, we compromised. We found out that elliptical wings are really nice, but oh God, they're so expensive to build. I mean, the Brits built in World War II with the Spitfire because everybody needed a job. And they could all go to work and build these things, the Hawker and the Spitfire. They built this beautiful wing, and came out really well. But for most profitable aviation companies, you can't afford to build this elliptical wing. So we build a tapered wing. And the tapered wing gets us up to, if you taper it just right, and you twist it just right, and you work out all the bugs and everything just right, you can get 0.95. So that's what we do. Go out there, look around. They're all tapered, right? And everybody out here is shooting for the mark, 0.95. And there you have it. So that's what we do with this wing design here. Based on experience, we're going to shoot for 0.95. Okay. So that's that. And I just have to include a picture of it because it actually is one of my favorite airplanes. Look at the elliptical wing. And then imagine building that wing as a sheet metal guy. But you got to admit, I mean, that is the most awesome. That is the most awesome wing there is. It's like art. The zero lift drag coefficient, it's really a big deal. And like I said, when that starts coming down, that induced drag starts being a big factor. So we've got to start paying attention. The Piper Arrow has a CD0, even though it has retractable gear and constant speed propeller, still has a CD0 of 0270. By the way, for the engineers, those are engineers know, those that don't, we call that counts. That's 270 counts, okay, typically. And so the Aero has 270. The Bonanza is 192. I bet you didn't know this. When you get into the Bonanza, and I'm not boasting about Bonanza, I'm just telling you the little details that you have to take care of to get these drag coefficients down this low. It's not easy. When you step into a Bonanza, there's a step that comes out of the fuselage and drops down below the trailing edge of the wing. Step on it in the airplane. When you close the door, turn the power on, the step actually retracts into the airplane. Now that's detailed. And that's the kind of stuff it takes to get 0.0192. That's pretty low. I don't know what's the CD0s on the composite aircraft, Todd? Do you know offhand? I mean, they're probably really low.
Probably 120.
I would guess, yeah. Now there is a little, black magic in the cards, because the CD0 is equal to the zero lift drag divided by 1/2 rho v squared s, the reference area of the wing. So the size of, you take a really, really clean airplane with really, really low drag, and you change the wing size a little bit, you change the value of that CD0 just by changing the wing size, even though it's remained just as clean, because the CD0 does have that reference wing area in the denominator. And this is something that is really confusing to students, and it takes a while for it all to sink in, because it really does sound confusing. It's not just a bold number, yes.
So that's for the whole airplane, not just for the wings,
the CD0 takes into account the whole airframe, including the wing design. Yes, takes into account everything. Yeah, the induced drag is the drag due to lift, which is primarily or totally a function of the wing design. The CD0 includes the drag of the wing, includes the skin friction drag, plus the drag where the wing meets the fuselage, plus the drag of the rivets, plus the drag of the static wicks, all the drag. Interference drag. We call that. We have all these little names for little types of drag: interference drag, pressure drag, form drag, parasite drag, skin friction drag. And what was the I think more?
Yeah, power cooling drag.
Yeah, cooling drag is another one. Okay, the Cessna 182. It has fixed gear with wheel pans in a strut. Its CD0 is 0.03.0. I'm going to try and stop here. Okay, design a high-performance single-engine airplane with the same useful load capacity, same stall speed, except, okay, we're going to put a high aspect, we're going to increase the aspect ratio, so we're going to put a higher aspect ratio NLF wing on it. That means natural laminar flow wing. Design and size for the aircraft. The new cruise performance and range will be recalculated using the same power loading or the same power plant. Okay, so taking what we know, we're going to put a new wing on it. For the given cabin, I'm just going to gloss over these. For the given cabin and fuselage, the wing is an important factor. Okay, for the light airplanes, the wings are typically very big, okay? And this is done to obtain low stall speeds, okay? We drag around way, way too much wing on all of these airplanes. Like I said, on all these airplanes, if you want to cruise efficiently, you would take out a saw and cut off half the wing. You don't need it. It's there to take off and land, okay? So, what we're going to do is we're going to compromise. We're going to put a wing on this airplane And what we're going to do is we're going to cut down the size of the wing. And we know that by doing that, that's going to affect the stall speed. It's going to make the airplane stall at a higher speed, and it's going to make it want to use more runway. So what we're going to do to counteract that is we're going to put a better high lift system on, like Todd suggested early on. We're going to put, instead of a regular flap, we're going to put a double slotted flap. Now, it turns out that when you put another little flap in front of a regular flap, you can, it's almost like a turning main. It drastically increases the lift. And if you put a third one in front of it, it increases the lift even more, but not as much as the first one does. If you put one turning main or one flap in front of one little, they call it a double slotted flap. You put one in front of your main flap, it really helps. So that's what we're going to do. We're going to put wide flaps on the wing. We're going to put a second flap in front of the first flap, okay? And in order to maintain our stall speed at 54 miles an hour, what we're going to do is we're going to cut our wing size way down, okay, to 150 square feet instead of the 180. So we're going to reduce the wing size. And what that's going to do is that's going to cut down the area of the wing quite a bit, so we're not dragging all this extra wing area along. And then, instead of using the original airfoil, which is a 23012, we're going to use a laminar flow airfoil. I don't know how many of you know a little bit about laminar flow, basically. Okay, well, you know that there's laminar flow airfoils. I used a 6 series airfoil as an example to compare for the calculations of performance. There are other airfoils that are better than the 6 series.
NLF 0414.
0414, I knew that. I should have, that's a good one. Did you design that one?
No, Jeff Beacon.
That's Beacon, okay.
And Werner Finisher.
So anyway, we're going to put a big, nice flap on this wing. We're going to make it a high aspect ratio wing. I'll show you pictures of it. And we're going to put a nice flap, high aspect ratio, cut the area down, and we're going to turn this airplane into, we're going to drastically increase the performance and range of this airplane. That's what we have. This is the basic airplane here. L over D max 14.4. Won't spend a lot of time here because we're running out of time. Aspect ratio is 6. Has 180 square feet of wing area, and I'm sorry, the stall speed's 56, not 54. So we are going to maintain the useful load, the takeoff gross weight, the horsepower, and the stall speed. And I haven't, you know what, I really don't have time for this either. This is just a little history of the Bonanza. And I probably ought to go ahead and jump right to the results. But I will say this, the basic airplane cruises at about 165 miles per hour at 65% power, okay? And if you're interested, these are some of the basic numbers that go into the basic airplane. The prop efficiency is about 0.85. And if you break down a typical mission profile, which you do when you have a lot more time and you're really working out the details, if you use the equations that I use, you can break down the fuel amount and the gallons of fuel for each segment of your profile and check and see that you do indeed have just enough fuel. If you burn that much fuel, you'll have just the right amount of weight left for the structure of the aircraft. And again, I won't spend the time, I don't have enough time to talk about all the structural stuff of all this, so I just kind of gloss over that. The wing loading is another way of expressing the size of the wing, okay? It's the aircraft gross weight divided by the wing reference area. And efficient cruise usually asks or requires a small wing area. Again, most of these airplanes carry around a wing that's too big. Short takeoff and landing, on the other hand, requires a large wing area. So it's a tug of war. Takeoff and land, big wing. Cruise, small wing. And we end up with some sort of compromise, okay? And what we're doing in here is redesigning the wing that can meet all of those parameters and satisfy all the requirements, okay? Everything is a compromise. We design as small effective wing as possible for cruise, and then we use the high lift devices to maintain that takeoff and landing performance. Incidentally, our new wing area, we have a minimum stall speed of 56. We will use, I have some flap data, we will use a double slotted flap, okay? It's going to be 80% of the span, okay? So most flaps are about 60%. This flap will span 80%, okay? And it'll have a CL max, a maximum lift coefficient of 2.8 instead of typically, I think the basic flap is about 2. And then we can calculate our new wing area. So using these numbers, which are actually pretty conservative, we end up with the new wing area. Comes from, again, that lift equation. We can actually do a lot with that. We end up with a new wing area here, 150 square feet. Okay? And then we take a look at using a laminar flow airfoil. And I just picked this one because data is readily available for it. It probably is for all the other ones now too, but you can go anywhere on the web and get data from the 6 series airfoils.
This is a balanced airfoil. Also, it doesn't build up pitching moment.
This one here.
Right.
Yeah.
Like some of the laminar ones.
Yeah, the laminar ones have
pitching moments get out of hand.
Right, right. And I mean, I thought the pitching moment ought to be like under, what do you think, under 25 to 0.25?
Yeah.
And I know some of those are like 0.40.
Yeah.
I don't know. And if you get into what we're talking about, some of these airfoils have pitching moments as well as lift and drag. This kind of gets into fairly advanced levels of airfoil design. And some of these airfoils can have rather peculiar pitching moment properties. That's sort of getting in a little bit of detail. This is, they call it the 6 series, okay? Whenever you see an NACA 6, okay, that means it's a 6 series airfoil, which is a laminar flow series of airfoils that Eastman Jacobs and others tested back in the 30s, I believe, in a low turbulence pressure tunnel. And a little bit about airfoils. NASA has a 4-digit series, a 5-digit series, and then early on the 6-digit series, and then there's a 7-digit series. And you can recognize the 4-digit series because they just have 4 digits, and the 5-digit series, because they have 5 digits. And of course, actually the 5-digit series, like the 23015, I was surprised how many. That's an old airfoil. You'd be amazed how many airplanes use the 23 series. One that I was surprised at, the C5 Galaxy, uses a 23 airfoil. I found out. And others. Pardon me?
Yeah, and also.
Yes.
Malibu, right there. All the RVs.
All the RVs use it?
All except the 9.
Really? Yeah, it's amazing. So.
There's a runs.
Really? Yeah, it's really, it always baffles me that, we have these, we've spent a lot of effort to improve our airfoil design, and we have, we've come up with some really great airfoils, but in many cases, we found out that there are these old reliable airfoils that really work great, and we still use them and will continue to use them in the future, so it's kind of cool. Here's some numbers. It's hard to get a natural laminar flow airfoil to work really well all the time, but the zero lift drag coefficient for a 23 series airfoil that's dirty is 0.100, and a clean laminar flow wing is 0.400. So this is readily available data on that airfoil, and you can see this is a lot of what we look at here, the drag data, and this here is this is what we call the drag bucket, okay? These airfoils have a drag bucket, and you want to design it so that you're cruising in this drag bucket, okay? And that's where the drag is the lowest, so we're down here during our, where we're designed to be cruising at, and we come over here and see we're only at 40 pounds of drag. It's really good, okay? Now this airfoil, you'll notice its thickest point is at about 50% of the cord. So it's a highly laminar flow airfoil, which is good for laminar flow but bad for some other things. But anyway, if this airfoil has a lot of bugs and contamination and everything else on the leading edge, you won't get much laminar flow. And look what happens if you don't have any laminar flow, your drag is way up here. So the really good performance of this airfoil is dependent on the laminar flow. And then, what's that?
Clean your wings and take off before the bugs.
Yeah. And then here's the, I was talking, this is, see about 0.025 on the pitching moment, a nice, kind of nice flat pitching moment line, and it's pretty manageable, you know. That's good for duck designers. If you're looking way ahead, you know, you don't want these really wild, steep pitching moment curves. I really don't have. Well, I will just say real quick, if you look at the airfoil, you'll notice that there's a little cusp on the trailing edge. You'll see this in a lot of laminar flow airfoils, the cusp. And the A, if you see an airfoil that says 65 A sub 2, that A means that they took the cusp out. And the story I heard is, we designed these 6 series airfoils, and the chief aerodynamicist at Piper said, I forget what they were designing, Malibu or something, called somebody up there and said, we can't build this cusp. I mean, it's too expensive. How are we going to make a cusp underneath the lower surface of the trailing edge and the flap, build it into the flap and everything? I mean, how could you guys have done this to us? And we said, oh, that's okay. We'll just spare the cusp in and make it a straight line, and we're going to, we'll designate that as the A series. That's the story I always heard.
Yeah, something like that.
Something like that, right? And so we have the A series that doesn't have the cusp, okay? And it causes, and you probably know this better than I do, you get some loss of performance when you take that little cusp out, believe it or not. But it's okay. And what else is there? Anything? You get a little change in pitch. It lightens up the pitching moment.
The pitching moment goes down.
Yeah, it helps that, but you lose the lift.
Yeah. At high altitude.
That's what I thought. And then the control forces, but that's another discussion. We're out of time. Anyway, that's the B-35 Bonanza. You put this, so you put this new wing on it. It's smaller, laminar flow, but much nicer wing. Really doesn't look all that much different, does it? There's the original wing. There it would be with the new wing. So you haven't really changed it all that much. Aspect ratio is 9.1 versus 6.1. I went from a 32-10 span to a 38-foot span, and it's tapered 0.4, and that's what the airplane would look like in a plan view. Okay. One other thing you want to take note of. See the flap? See the flap right here? Okay. The flap now goes from here all the way across over to here. So you have a much bigger flap now. Okay, so we have to do that because we want to stall at 56, and we can't install a 56 with that old flap. So we have to make some changes. So, but wait till you see the performance changes. We have the old fuselage, and you know what? I really don't have time to go into I went into the fuselage, the design of the tail, all these things, but I really don't have really the time to cover that. I will just say a little bit about the flaps, though, because this is kind of important. Different flaps have different values of maximum lift. So on the right, I showed you what the maximum lift coefficient is, okay? And a plain wing, clean, is, well, 1.6 is, really I should have just said 1.6. 1.6 for a basic wing, a plain flap, 2.3, and then you put a little slot in it here, a little slot here, you get up to 2.5, and then if we don't go with this type of double slotted flap, which has, sometimes I call it a turning vane, because it looks more like a turning vane than anything else, you get up to 2.8, and then if you go into the, you know, the big airplane DC-10 or Airbus flap, they have triple slotted flaps, and they're all the way up here to 3.2. So that's the maximum lift coefficient. Now, over here, if you're flying along at 56 miles an hour, okay, and you have 150 square feet of wing, this is how much lift you will get from these configurations, okay? So the airplane we have, the gross weight is 2650, so we're right here. We produce the lift equal to the weight, 2650. This one here would produce 3028. If we didn't have any flaps, we'd be down there at 1643. So it makes a big difference. You go from 1643 pounds all the way up to 2650 pounds and dropping those flaps down. So it's a lot of lift. So you got to have them, or you get hurt. So anyway, that's a little bit about the different flaps. And then the other question is, well, you know, that they're complex. Are they going to make the airplane really heavy? And the answer is that flap will add about 1.5% to the takeoff gross weight. So yeah, it will add a little weight because they're 8%. They're an extra slot. So yes, it does add weight. So I think it adds 45 pounds of weight. That's what I calculated. So you can have that little bit cavity.
How much weight did you lose?
43 flaps. I'm sorry?
How much weight did you lose for the wing area reduction?
I believe that wing, I didn't take into account using the modern materials and composites. I figured that wing would be built lighter than the original wing because of modern materials, so I just used the same wing weight.
Also, while the area goes down, because the span is longer, the spar will get heavier.
Right.
Because of the increased bending moment.
Right.
So they kind of
I figured
wash back and forth.
I figured it all would probably wash out, or if any, there would be a net benefit when you're all done. In the worst case scenario, it would come out even. And so I didn't really spend a lot of time addressing all that. Okay, so that's about it. Of course, the performance is the main thing. So what happens when you take this new wing, put it on the airplane? I mean, that's what it's all about, getting a better airplane. So these are all the numbers. The original airplane goes 164 miles an hour. And if you calculate all the drags, you end up with 236 pounds of total drag and requires 117 horsepower. The new design will cruise at 196 miles an hour. That's a lot faster. And its total drag is 205 pounds, and the power required is 121. You might ask the differences in the numbers and all that. The power required is equal to the drag times velocity, as many of you may know. So, you know, if the velocity goes up and the drag goes down, you still have the same power required. So, anyway, that's why the velocity is higher and the drag's lower. They're just bouncing back and forth. So, anyway, yeah, the new wing now will give you the same stall speed, and you can cruise 32 miles an hour faster. And because of that, of course, your range is going to be, this is the same power setting, the fuel burn will be the same, 10 gallons an hour. but your range is going to be much further. So this is just a program I have, by the way. I estimated all the weights of all the components, okay? Just to show you that I actually did a structural analysis briefly just to check everything. Anyway, more on analysis of the structural weights, okay, but we won't spend a lot of time on that. Again, I have some stuff on all the stability and control. We don't have enough time for that either, but I can just guarantee you that this aircraft is stable and has a sufficient, as you may know, sufficient static margin, both statically and dynamically, to be stable throughout its control flight envelope. Okay. Anyway, this is a summary of the overall performance. Okay. The airplane cannot cruise at its L over D max. The wing has to be way too small to do that. The wing has to be about half its original size. So instead of being 180 square feet, it's actually got to be less than 90 square feet. So we can't cruise at L over D max any more than any of these airplanes can cruise at their L over D max. You know. So, but our L over D max is 19. We're 17. 196 miles an hour, just shy of 10 gallons an hour. And our range, because of that, is now 820 statute miles, and originally it was 600 statute miles. And those are the final performance numbers, CD 0.0150. So anyway, in summary, we did kind of an overview, brief. Didn't really do a conceptual design, but just maybe got a chance to talk about a lot of the things that, if you're working on anything like this, maybe just a discussion like this might help you a little bit. We increased the cruise speed, we increased the range. I promised I'd say just a few quick words about us over there in Morgantown for anyone that may have anybody interested. We do have an aerospace program. Actually, I'm very pleased to see one of our professors, Eli, here. Thank you for coming all the way from Morgantown. It's nice to have you. We have an aerospace program. I teach there, and we have 419 students, 27 faculty members. We have an active research program. If our students, one of the things they do is they design, build, and fly these rather large airplanes, and they compete in an international competition. And last year they placed in the top 10. So even though you might think that we're over there in West Virginia where it's, you know, mountainous and cold country, we actually have a very active aerospace program, very ambitious, enthusiastic students, and we do a lot of research. We have models that get tested, and there's a 757. We have very large F-22 Raptors. We fly them in formation, and we do a lot of really cool stuff. So, you know, if anyone ever wants to visit there, give me a call. If you want a copy of this presentation, if you can leave me your email, I will be glad to send you that. And I will give you mine if you ever have any questions or anything, if I can help you in any way. Please don't hesitate to give me a call. I'll be glad to help you out whenever you may need. So, yes, any questions you may have?
I just wondered, would you be able to get the original landing gear in that wing and the new wing, or would it have to be different landing gear?
To be honest with you, I did not, you know, actually look at the details of the landing gear going into that wing. So, you know, an honest answer is I don't know. But the wing, maybe, yeah, not quite as thick. But the wing, yes, I just don't know. The wing looks like there's ample room, but I don't know.
That landing gear takes ample room.
You know what? It does, doesn't it? Because of the system. Right, so that's a good point. Yes?
How do you suppose the small ailerons affect the low-speed rollover?
Well, actually, that's a great question, too. Sometimes when you put small ailerons on an airplane, there can be a problem, and if there is, it's usually supplemented with spoilers. 99% of the time, the addition of spoilers always solves the problem. Which actually leads me to a story, not really a story, an experience. In the large Airbus, we have ailerons and spoilers, as most large aircraft do. And it's really interesting to fly that airplane. Just like, I shouldn't use the word fooling around, but if you fly the airplane, if you turn off the hydraulics to the spoilers, you make a turn. You know, well, actually has a side stick. You make a turn with just ailerons, and it's this very slow, sluggish turn. You know, it's almost like something happened to the aileron control, and then you turn the you turn the spoilers on, and then all of a sudden it's just like turns on a dime like that. It's just amazing the power of the spoilers. I would say most of the roll control comes from the spoilers in these airplanes.
It's spoiling on the inboard wing? On the inside wing, rather?
Well, yeah, the spoilers, you know, come up on the inboard wing. Oh, I thought you meant inboard or outboard spoilers. I'm sorry. They actually have inboard and outboard spoilers that run off separate hydraulic systems. I think there's a total of 4 panels, so it's quite an elaborate system. It's not just one spoiler, you know, it's many. So, yes.
Is there data on how the scale matches their scale report? You don't see any double slotted planes out there.
No. Yes, there's a lot of, I know we have a lot of research papers from Langley on the double slotted. They did a lot of Reynolds number research.
Well, they got data. It depends on the airfoil.
Yeah.
Now, some airfoils, they have data all the way down to 500,000.
Yeah.
Not all airfoils, but some airfoils and airfoil flap combinations, they did go all the way down to 500,000.
That's a good question. Yeah, I'm not sure. I don't know exactly the Reynolds numbers.
You usually won't find that in period wing sections.
No.
But if you go into the references that period wing sections has, you can sometimes find those low Reynolds numbers in the references to period wing sections.
On home built, I've never seen anything other than a slotted flat. I've seen double slotted flats on the walkers.
Stuff like that. I can look for you.
The Swearingen used that.
Double slotted?
I think. I know there's at least one slot.
Oh yeah, there's a number of them that are slotted.
Double slotted. Look at the Swearingen. He did exactly what he's talking about. The little S6
give you a
30
booster that scale maps. I'll be glad to look for you and see what I can find. I know the guy Langley that did the testing.
And budgets here for just other numbers on
It's more, double sided is more expensive. It's, if you get it out of grid, it could be more sensitive. Those small pieces. If you get out of grid.
Did you use a slat instead? Leading edge slat instead?
I'm sorry, what's that?
Instead of the double slat, did you use a leading edge slat like the
You know what? I didn't address slats because when you're using natural laminar flow, the slats tend to kill
That was
it.
the other half of the question.
Yeah, the slats tend to kill it.
If they retract very cleanly, it would work.
Yeah, you need a clean leading
It's a
edge.
mechanical problem, just to get it really clean would be the problem.
It'd be a tough one to solve.
Like the laminar flow clean wing concept.
Well, what I'm saying is that slat would be very difficult.
Oh, yeah,
Just
yeah,
to
actually-
get mechanically, just to get the flow, so it is smooth.
Yeah, you know what? It's actually impossible.
There were
The slat is almost makes it impossible. We tried a couple
During-
things and
during
it's almost just doesn't work.
during the airline natural laminar flow program at NASA Langley, there was a whole study done on how to do leading edge slats for airliners without messing up laminar flow.
Yep.
And it was not easy.
Yeah.
It was very difficult.
But you know what? I was out. I just gave a talk out in France at a convention, and Airbus now is going back and revisiting all that natural laminar flow on airliners, and they are going back and looking at all this stuff with a whole different point of view. They're gonna try to get to laminar flow on transport aircraft, and they're already looking at it now on the tail. On the tail, you don't need the leading edge devices and slats and stuff on the elevator. So they're looking at natural laminar flow on the tail as we speak, and they're really gung-ho with this. I didn't get a chance to tell you that, and I was in Nice, France, talking about it not too long ago. It's interesting. Yeah, it's really interesting. Yeah. What's that?
I thought most of that work was done in England.
Well, on the main wing, yes. But the French and the Germans that make the tank.
You know what? I don't know. This is just.
But the main wing work for Airbus is in Britain.
Oh.
But the tail is either German or French.
See, I'm not sure. This was at the ICAS conference.
Yeah.
Conference.
Huh. They actually not work on a main wing, right? Actual laminar flow?
No, I'm saying all the Airbus main wing work.
Oh,
It's done by the British.
Oh, it is?
Yeah.
It is, okay.
All that high lift devices and all that.
Oh, it is. I didn't realize that.
Yeah. Whereas the French and the Germans, and the Spanish and the Italians, do the fuselage,
Yeah.
the tails, and the landing gear.
That's a whole European story.
All the other pieces.
Any other questions before? Yeah. Clark, yes.
The airfoil section you showed up here had a pretty sharp stall rate. What would you do to mitigate against that?
You know what? The NLF 414 airfoil has a much rounder leading edge.
No, sharper. The 0414 had a very sharp leading edge, and they were shocked at how soft. And it was the way the boundary layer developed and transitioned and went over the upper surface. It's very touchy. You can make mistakes there.
There's a couple things you can do. One is, that's a 65 series airfoil. There's also 63 series, and there's other series. But the thing to do is look at the different Reynolds number ranges where your aircraft is stalling at, because that has a huge effect on the stall characteristics and properties. The Reynolds number that you're at may not have that start breaking the stall. So the first thing to do is look at the Reynolds number and see what you actually have, and then look at other airfoils that are close to that Reynolds number and see what their characteristics are, while still giving you mainly a decent amount of laminar flow. And you got to watch that pitching moment curve too, because it's also not only the flat part of the pitching moment curve, you got to watch that pitching moment curve when you get to the stall. And sometimes it'll really take off and give you a real sharp pitching moment. Real sharp.
Do you remember the VMAX Pro?
So that's about the best advice I can give you without having a whole bunch of stuff to look at. Yeah.
Do you remember the VMAX Pro?
No.
He wanted to set a bunch of records for his weight class.
Yeah.
And he crashed. He used the 0414. Yeah. He made a mistake. And where it bumped out a little bit because he miscalculated the thicknesses of the pieces as they went together at the trailing edge squat. Now, I personally think that because he was near stall and he snapped it, and I personally think, I have no direct evidence of it, but I personally think that it was a manufacturing error that caused that snap to happen, because he did have a manufacturing error on that wing that used that 0414 wing. And you got to be real careful. You got to really make it as the specimen, the coordinates call out for it. if you deviate from the coordinates, the boundary layer will do things you don't want it to do, and the performance falls off. It can fall off rapidly.
Hey, they just gave me the signal. I gotta